Okay, so this is the last section in our calculus chapter, and then I will have review stuff for you next week. So this is called optimization, and this is an application of calculus. Now, it's doing something that you've done before, just doing it in a slightly different way here. What we're doing is we're looking at this as something that we want to find a minimum value or a maximum value. And we know how to find minimums and maximums because we did that in the first part of this chapter where we find our increasing and decreasing values. So some tips for solving optimization problems: draw a picture if applicable, assign your variables, know what the variables stand for, write an equation that's to be optimized in terms of two variables. Now this is not something that, write your equation that's going to be optimized. Find values that make sense where the derivative is equal to 0. If you end up with a negative answer, sorry about that. If you're coming up with a negative answer and you're talking about a side or the number of items that need to be sold, obviously that answer doesn't make sense. And then, this last part doesn't apply to us. But do remember to check the endpoints if you have a closed interval. That's not something that I think is in your homework, but that would be something like if they said that you were only allowed to sell 20, then maybe it turns out that 20 is the number that you want to use. So just like your absolute minimums and maximums, sometimes those are the numbers that are your absolute mins and maxes, are your intervals there. Okay, so example 1, the cost of making n tennis rackets each day is given by the function C of n is equal to n squared minus 20n plus 120, where C of n is the cost in dollars per racket. How many rackets should be made per day to minimize the cost? So this is what tells you that you're going to need to essentially do a derivative. And what is that minimum cost? So first we're going to find that derivative, and we're going to set it equal to 0 and solve for n. So C prime of n would be, here's what we're finding the derivative of, 2n minus 20. Okay, so that's pretty easy. Now set it equal to 0. What's going to give me that minimum value in this case? We're going to add 20, and we end up with n equals 10. Now, normally I would, verify that this is a minimum. If it was a minimum here, then that means the graph's going to be decreasing, which means the left of 10 will be negative, and decreasing, the right of 10 will be positive. But here's the thing. For anything that we're going to have to do, if they ask you to minimize, the number that you get as an answer will be a minimum. And if they ask you to maximize, the number that you get as an answer will be your maximum. So you really don't have to worry about it. But if you're concerned about that, you could do that. This is in this case it would be C. C prime of n. If I plug, again, a number in to the left of 10, I end up with a negative. Here I end up with a positive. So, hey, this is a minimum value. But, like I said, it'll be the way it's supposed to be. Now, to find the minimum cost, I need to plug that back in. So, C of 10 would be 10 squared minus 20 times 10 plus 120 ends up giving me $20. So that's the cost of making tennis rackets each day. So the minimum that we can make that would be, the minimum would be $20, and that's by making 10 rackets. Okay. Next. Okay, this one's a little bit more complicated. We have a rectangular plot of farmland enclosed by 180 meters of fencing material on 3 sides. The fourth side of the plot is bounded by a stone wall. So find the dimensions of the plot that enclose the maximum area, and then find the maximum area. So even though this one's asking you to do a maximum, you're going to do the same thing in general, but it is a little bit more complicated. Now, first of all, to find the area, well, let's talk about our picture first. So here is my stone wall. And so we're using part of that wall as a boundary. So when we draw our rectangle here, we only have 3 sides to worry about. So with a rectangle, of course, your opposite sides are congruent. So in this case, the two shorter sides there are both x, and then I made the longer side y. Totally your opinion which side you make what. But I don't need to put a y on the other side there because I don't need to put a fence there, okay? Now we're trying to maximize the area. So just up here at the top for a minute, I'm going to write that my area would be x times y. That's what I want to find the derivative of because I want to maximize that. But I can't. I can't do a derivative that has two letters in it. Well, there's also this fence. All right, so the fence, I only have 180 meters of fence. So if I want to maximize the area, I mean, just keep making the sides bigger and bigger and bigger. That's going to maximize your area. But I can't because I'm bounded by how much fencing material that I have. So let's think about the fencing material first. I have 180 meters of fence. The fence goes around the farmland here, which has to do with perimeter. So if I want to find the perimeter of my fencing, in this case that would be x plus y plus x is 180 meters of fencing. So 2x plus y is the amount of my fence. Now, the area is x times y. What I'm going to do is I'm going to take that fencing formula and I'm going to plug it into the area since they're connected. Now, I can plug it in however I want to. I'm going to do substitution. I can either solve this equation for x or solve it for y. Well, it'd be a whole lot easier to solve it for y. So y is equal to 180 minus 2x. Okay, so now I'm going to come up here to my area. So my maximum area is equal to x times y. Well, that's really going to be is equal to x times 180 minus 2x. And I'm just going to call that A for my area. Okay, well, let's go ahead and multiply that out. 180x minus 2x squared. And now I'm going to find the derivative. Because that's what you do when you maximize. And now that I only have one letter, I can actually do that. Okay, so this process here, this is definitely a more complicated question. This is going to be like if you write that formula for what needs to be maximized, which in this case was x times y, if it has two different letters in it, then you're going to have to do something along these lines. Okay. So set that equal to 0. I get 4x is equal to 180. X is equal to 45. Now, the question says, find the dimensions of the plot, find the maximum area. Okay, so the dimensions of the plot, well, I can plug this x in here to find y. So y would be 180 minus 2 times 45, which turns out to be 90. So my dimensions would be a 45 by 90, 45 meters by 90 meters. My area then would be 45 times 90, which should be 4,050 meters squared. Now, you may not always be asked to find the dimensions and the area, so just find whatever it is that they've asked you to find, but you should be able to find both of those. All right, another pretty typical question is we have a square piece of cardboard that measures 15 centimeters on each side, has, oh goodness, 4 identical squares cut out of the corners so it can be folded up to make a box with an open top. So here, this whole thing here is 15 all the way around, but when I go to fold it up, and you kind of have to visualize this here, this would be x. This is, all of these are x's here, okay? X here, just x's all around. What that means is that this dimension right here is actually 15 minus x, and then the dimensions on the side is 15 minus, sorry, not minus x, minus 2x. The whole thing's 15, but I'm getting rid of an x on each side of that 15, so we're taking 2 x's away, okay? So here is my length, if you want to say, here is my width, and the height, when I go to fold the box up, is actually x. Okay? Now, why do we have to think about all of that? Because it says volume, and volume is length times width times height. So find the dimensions of the box that gives the maximum volume, calculate the corresponding volume. So I'll find the dimensions of the box once I figure out what x is. So my volume is length times width times height. So in this case, and it's of course up to you what you think of as length and width and height, but the volume is going to be 15 minus 2x times 15 minus 2x times x. Now I'm going to multiply the two 15 minus 2x's. Make sure that you do the distributive property and so on and so forth. I'm going to shorten that one here. It would be 225 minus 60x plus 4x squared. If you need to show more work, you'll go ahead and do that. 225x minus 60x squared plus 4x to the third is equal to my volume. Okay, now the volume is what I want to maximize. That only has one variable in it, so I'm good to go. We're going to find that derivative and we're going to set it equal to 0. So v prime would be equal to 225 minus 60x plus 12x squared, and set that equal to 0. Now, I need to solve that. So we could use the quadratic formula, we could factor it, we could use our calculator. I'm honestly not sure that this factors. Actually, no, it does factor, but it's going to be a harder one to factor. We can't, unfortunately, get rid of that 12 in front of the x squared. What I'm going to do is I'm going to go ahead and rewrite this, because this is really the way that we need to think about this equation. Okay. And I'm going to go ahead and put it in the calculator. If you're going to have a graphing calculator, you might as well use it. So I'm going to go to apps and get rid of this stuff here. Sorry. We're going to use number 4. Now yours will be a different number, but it's that solving app. We want to solve number 1. The simultaneous equation solver, that's when you have a system. So we want number 1, and everything should stay on this page the way that it is. Hit next. Now again, yours might look a little bit different than this, but we're going to type in our variables here. It's going to be asking you for the same stuff. It just might have you fill it into the actual equation instead of doing it in a list like this one is. So that's going to be 12, that's going to be negative 60, and that's going to be 225. Okay. Then we're going to hit solve, which is the actual graph button here. And something's not right there. So let's go back here and see what happened. Let's see. 12, negative 60. Well, oh, I see what happened. I have a typo here. Let's go back here. Okay, so when I found the derivative, I didn't find the derivative of the middle correctly. So this here should not be 60. It should be 120. I had to change this question originally, and so I think that's what the problem was. I just forgot to change it here. Okay, so hopefully the rest of this is not a problem. So let's go back again. And again, the problem was, so here, 225, here that 2 has to come down in front, so that's 120. Here the 3 comes down in front, so that's the 12. Sorry about that. Okay, so now, negative 120, and solve. Here we go. That's how it was supposed to come out. So 15 halves and 5 halves. Now, really we want exact answers. Those luckily are numbers that we can change to a decimal pretty nicely. If you can't, depends on the the way the question is worded there. You might be able to round it, but I would honestly try to not. So 15 halves and 5 halves. So let's come back here. X could be 15 halves, or x could be 5 halves, which is 2.5, which is 7.5. Now, how do we know which one? Well, plug them in. Maybe one of them doesn't make sense. So 15 minus 2 times 7.5 is 15 minus 15, which is 0. So this answer doesn't make any sense. Now, you can verify the other one, but the other one is good. That's going to be 15 minus 5, which is 10. So that's good. That also gave us one of our dimensions there. So the dimensions now is a 10 by 10 by 2.5 because my dimensions were right here, length, width, height. Okay. Now for my volume, now you just multiply those three numbers together. 10 times 10 is 100 times 2.5 gives me 250 meters cubed because we're dealing with volume. All right. One thing back on this real quick about the mistake that I made. One thing that would be helpful to do, and I actually really thought about this before I started working the problem out, is that we should have the thing we're taking the derivative of right above it. I tell you that though, but at the same time, on my notes that I typed out, they're written that way, and yet I still made a mistake. So, all right, last one. This one isn't necessarily an optimization type of question, but it's in this chapter, and it's a good question in my opinion, which means definitely it's something you could see again, whether it's on my test or the test. So we have a function g defined as g in terms of x gives me px squared plus qx plus c, where p, q, and c are members of the real numbers. So if g of x is equal to negative 4x plus 12, let's find the values of p and q. Okay, so here's my equation, and here is the derivative of my equation. Okay, well, let's find the derivative of the equation in the box there, okay? P and Q are numbers, so if I bring that 2 down in front, that's going to be 2px, okay? Q is a number. If I take the derivative of qx, that's just going to be q. C is a number. When I take the derivative of a number, it becomes 0. So that's my derivative. Now, set that equal to what they told you the derivative was. So 2px plus q is equal to negative 4x plus 12. Now, in this case, it should be pretty obvious that q is going to be 12, and then these two are going to get set equal. Okay, q is 12. 2px is equal to negative 4x. Well, really, you get rid of the x's. We just need the numbers in front of the x's to be the same. So p is equal to negative 2. So all it said there was to find the p and the q, but if I need to find my actual equation, I'd plug that back in. Now, we actually are going to need to do that, so let's go ahead and do that. So that's going to be negative 2x squared plus 12x plus c. Now, I don't know what c is, but we're going to work on that in the next part. Okay. Now, if g has a maximum value of 5 at some point a, find the value of c. Okay. Now, if I knew what point a was, then I could find the value of c. Now, remember that your maximum value happens where your derivative is equal to 0. So the maximum value, they're telling me the y value. They're not telling me, though, where the y value happens. So I'm going to go back to my derivative again. G prime of x was equal to negative 4x plus 12. They told me that. I'm going to set that equal to 0. To find out where does it have a maximum value. Not what is the maximum value, because I already know that. Where is the maximum value? So negative 12 is equal to negative 4x. X is equal to positive 3. So my maximum happens at the point 3, 5. Now, what that also means is that 3, 5 is on my original equation. So I can plug that into this and get my answer. Okay? So I'm going to write y equals, technically this would be g, I guess, but of course they mean the same thing. So 5 is equal to negative 2 times 3 squared plus 12 times 3 plus 5. So 5 is equal to 9 squared, 3 squared is 9 times negative 2 is negative 18 plus 36 plus, sorry, I got a little ahead of myself there. That shouldn't be a 5, that should be a C. plus c. That's 5 is equal to 18 plus c. C is equal to negative 13. So that's all they asked me for, but that means that my actual equation now would be that. Okay. All right, so that's it. We did actually quite a bit of calculus in here, just on a simpler level. We just learned one type of derivative. There are actually several types, but we did the simpler type. Okay. All right.